Hey, welcome back, everybody. We're starting a new unit today, and it's a unit that focuses on the electron as probably the single most important subatomic particle that we find in the atom that controls so much having to do with the properties of an atom and the reactivity of an atom, etc. But as we saw in our movie the other day, a fine understanding of the electron really requires an understanding of something called electromagnetic radiation, which is a type of energy that is ubiquitous. It's everywhere and comes in many forms. When we think of, or when I think of electromagnetic radiation, the very first thing I think of is light. And light, visible light, comes in many forms itself. If you take what we call white light and you pass it through a prism, that white light will separate into all of the colors of the rainbow, producing what's known as a continuous spectrum. That continuous spectrum has all the reds and all the blues and all of the colors that you expect in the rainbow. Nothing's missing, and that's why we call it continuous. What our movie showed us is that, and why we need to talk about light as we approach the subject of the electron, is that there are circumstances where you can produce a spectrum that isn't continuous. That if you take a gas, specifically if you take a gas of a an isolated element, for instance, something like in these two pictures, sodium and hydrogen, and you heat up that gas and you view the light that is emitted from that heated gas, what you'll see is that that light separates, but it doesn't separate into a continuous spectrum. It produces what's known as a line spectrum, and later we'll come to call it an atomic emission spectrum. What we'll also come to find, as was reported in our movie, is that these line spectra have everything to do with the electrons within the atom. It's the electrons that are producing these specific lines of color. So I think understanding something about light is really, really foundational to understanding electrons. So let's talk in general about electromagnetic radiation. I think we get caught up in the visible part of the spectrum because it's what we can actually see. We're used to seeing the colors of the rainbow, but the truth is, visible light is just one piece of a much, much larger spectrum, um, and most of it is invisible to us. But it includes some things that are familiar to us. When we were talking about nuclear chemistry, for instance, we learned about really high energy gamma rays. Gamma rays are on one extreme end of the electromagnetic spectrum. I think we should actually write that this side of the spectrum is the high energy side. And even though we haven't defined it yet, let's talk about wavelength for a moment. We're going to find that that's an important component of understanding light and how it's made. The wavelength of a gamma ray is really tiny, 10 to the minus 12 meters. So let's write small wavelength on this side. And we're going to learn about something else called frequency. And frequency again, we'll define it later on. That's a really large number, a large frequency. So let's list that as high frequency. So on one extreme end of our electromagnetic spectrum, we have gamma rays, which have small wavelengths, high energy, and high frequency. As we move to the right on this spectrum, there are things that become less energetic. They start to have longer wavelengths and lower frequencies. So X-rays, for instance, are going to be a little bit longer wavelength than a gamma ray. They're going to be a little bit lower energy. They're going to have a lower frequency as well. They're still very energetic. We know that we can use them to we can pass X-rays through flesh, take a look at bones that might be broken. Still in the high energy category is ultraviolet light. We know its potential to cause sunburns if we stay out in the sun too long. Right in the middle of the spectrum for us is the visible part of the spectrum. One of the things that I want to note is that the colors of the rainbow also have different energies and wavelengths and frequencies. And so what we'll start with is we'll say that on the blue side, that is the high energy side of our visible spectrum. So let's say that's high energy. And the red side of the rainbow is going to be our lower energy visible light. And then energy that is even lower, or I should say radiation that's even lower in energy than red visible light is infrared. And then below that, microwaves and even radio waves. But on that end of the spectrum, we should note that the wavelength is much, much longer now, maybe as long as a meter or so. So we're going to say long wavelength. But we're going to also say higher energy on this side, or excuse me, lower energy, the lowest energy. And we're going to say low frequency as well. Okay, so let's define some of those ideas a little bit more than we have to this point. When we look at electromagnetic radiation, it actually travels as a wave, very similar to, an ocean wave or a sound wave. And there are characteristics about these waves that we can measure and quantify. And probably the two most important things that we look at are what are called wavelength and frequency. The wavelength is really just the distance between any two similar points on adjacent pieces of the wave. So if I measured the difference or the distance between this peak and this peak, that would be equal to one wavelength. But if I measured the distance from the trough to the next trough, these waves are regular, and so that distance should be exactly the same. Likewise, I could measure from the middle of this wave to the middle of the next wave and get the same length. Because wavelength is a length, we would expect that the units for wavelength are going to be something like meters, but oftentimes there's some derived unit of meters. So you might see nanometers or micrometers or centimeters or something like that. Frequency is a little bit tougher to talk about. Yeah, when I think about frequency, I think about counting things. So if I was standing at the ocean and I was counting every time a wave peaked, crashed on the shore, and I measured how often that occurred over, let's say, a minute of time, then I would be measuring its frequency. And so, typically speaking, a a wave that has a really long wavelength, if it's traveling at the same speed as a wave with a short wavelength, the long wavelength is going to have a very, very different frequency, a much lower frequency than the short wavelength. So think of these two waves down here at the bottom. The first one, 800 nanometers, is a long wavelength, but if I were counting wave peaks, it would have a really low frequency. On the other hand, 400 nanometers is a pretty short wavelength, and it has a pretty high frequency. Frequency has a weird unit. Sometimes people will write it as something called a hertz, but in this class, for the most part, we're going to say that it is equal to 1 over a second. How often does something occur per second? Think of it that way. The one thing that we don't talk much about in this class is amplitude. And amplitude is just how tall is the wave. And you can think of that as changing the intensity of light. But for the most part, for a chemist, it's not something that we address in great detail. Okay, I think we'll stop right there and we'll come back in our next video and look at the relationship between wavelength, frequency, and then we'll talk about, for the first time, how fast these waves actually move. Okay? All right, see you next time.